All right, we're getting to 8.3 now. So the next couple of sections are going to be more trigonometry based, just because those integrals can be difficult. So for this section, though, it's kind of a mix of a bunch of different types of things, and mostly we're going to be using these identities. However you spell it. Here we go, to transform integrals. So the first thing we're going to look at is going to be products of sines and cosines. Basically integrals that are in this form. So any integral that is sine to some power times cosine to some power dx. Now, they may not have a sine in it. It may not have a cosine in it. These powers may be 1, 2, 3, 4, whatever they may be. They may be the same. They may be different. So just any combination of sine to a power or cosine to a power or the two multiplied together, two powers. All right, we're going to break this down into two cases here. Well, I guess three cases. All right, so three different cases here. The first case that we want to look at is, let's look what happens if the exponent on the sine is an odd exponent. If the sine does have an odd exponent, regardless of what the exponent is in the cosine, or even if there is a cosine, we're going to do a little clever trick here. This is something that's very popular in math. Anytime we denote something as being odd, we could rewrite it into the format of 2k plus 1 for some k. This always comes out to be odd regardless of what the k is. So given an odd number, I could easily find the k here. So maybe if the m was 5, the k would have to be 2, because 2 times 2 is 4, plus the 1 is 5, and so on and so forth. And then what we're going to do is we're also going to use the Pythagorean identity for sines and cosines. Rewritten a little bit. So we're just going to solve it for sine squared and write it as sine squared is equal to 1 minus cosine squared. Okay, from there, what we're going to do in our integral, there he goes, is we're going to take that sine m to the, sine to the m power of x, and we're going to substitute in that 2k plus 1. So now it's going to be sine to the 2k plus 1 of x. And then what we're going to do is we're going to break that up. We're going to write this as sine squared of x all to the k times just a regular sine of x. Okay, so that's using a couple of different rules here for exponents. First, the product rule. Anytime you have two exponents added together, you can break that up into the two things multiplied together. So sine to the 2k and then sine. Then using the what's it called, the power rule of exponents, sine to the 2k, we could rewrite as sine squared to the power k. All right, so that's just using some exponents here. Finally, we're going to use the Pythagorean identity. And rewrite that sine squared into 1 minus cosine squared. Okay, the reason we do all that is that now this is something we'll be able to integrate out. So from here, we use u substitution. Now I know it might not look like it'll work out, but I promise you it'll work out. If you let u be cosine, then du would be a negative sign. Oh, sorry about that. And then that means that sine x on the end here would come out with the du. And then we'd have 1 minus u squared all to the k, and that is something we'd be able to do. All right, let's look at the other two cases first, and then we'll look at an example of each one of these. So case 2 here. So case 2, what happens if the m, so the exponent on the sine is even, but the exponent on the cosine is odd? I'm just going to write that we're going to do the same thing, but replace the cosine instead. So it's the same exact structure to this case 1 here. It's just that we're going to solve for the cosine squared and substitute that out instead. And when we look at an example, you'll see what to do. So finally, case 3. What happens if both the m and the n are even and we do not have an odd exponent anywhere? If this is the case, we're still going to do a trig substitution, and it's kind of a weird one. Substitute. We're going to use this trig substitution. I guess there's two of them. So sine squared of x is going to equal to 1 minus cosine, not squared, sorry, cosine of 2x, all divided by 2. And we're going to use cosine squared of x is equal to 1 plus cosine of 2x, all divided by 2. Okay, so these come from the double angle identity for cosine, and you can look on the trig identity sheet to make sure that this is the case. But these are their substitutions. Sine squared is 1 minus cosine 2x all over 2. Cosine squared 1 plus cosine 2x all over 2. So I'll come back to these cases, and we're going to look at a couple of examples now. So I'm going to go over to OneNote so I can write them all out a little bit better. Hold on, let me reposition here. I have my laptop flat so I can actually write stuff out. Let's look at these first examples. So the first example I want to look at is the integral of sine cubed x cosine squared x dx. Alright, so this is going to be case 1 because we have the odd exponent on the sine. Case 1 and case 2 are pretty much identical to each other. As long as there is an odd exponent on either a sine or a cosine, you're going to use the same trick. The trick is we're going to rewrite sine cubed by pulling out a single sine. So pulling it out is going to leave us with a sine squared, a sine, and then we still have this cosine squared floating around. Then, whenever you have that single one that you pulled out, you're going to pair that with the dx, and then rewrite everything else in terms of cosines. So this sine squared, I'm going to rewrite using the Pythagorean identity as 1 minus cosine squared. This cosine squared I'm just going to move over, and then the sine x dx I'm going to put on the end, because that's going to be my substitution. You can distribute the cosine squared into there if you really wanted to. It doesn't really matter. All right, from here, the u substitution. And you have to be careful with what you let the u equal to. We are just going to let u be cosine x because the du, which is negative sine x dx, will cancel out with the sine x dx that I already have. So I do have this negative sign. I'm just going to throw that negative sign all the way in front of the integral. Cosine squared is now u squared, minus cosine to the fourth is now u to the fourth. And then the sine x dx is going to be du, the negative sign I moved to the front. Antiderivative now, so negative u squared is going to go to 1/3 u cubed. This negative, I'm going to go ahead and cancel out with that negative and make it a positive, and the antiderivative 1/5 u to the 5th. Don't forget the plus c. Finally, redo your substitution. Remember, u is cosine. Oh, jeez. Sorry. Completely spaced there. Plus c. And there we go. So that's going to be my antiderivative. If you did take the derivative of this, negative 1/3 cosine cubed x plus 1/5 cosine to the 5th x plus c, I promise you it would end up being this up here, the sine cubed cosine squared. Okay, still a little bit of time. Let's do one more example here. Let's look at the integral of just cosine to the 5th. All right, so we can now do antiderivatives like this using these cases. This is going to be case 2. We have the odd exponent, but this time it's on the cosine. So we're going to do the same trick. Our trick is we're going to pull out a single cosine and write this as cosine to the 4th, and then just a cosine that we pulled out. And then this cosine to the 4th, we're going to change into sines. To do that, we have to do a little bit more work. You want to think about this cosine to the 4th as cosine squared, all squared. So this is like pulling that k out of the exponent using the power rule. Then the cosine squared in the parentheses, we're going to change into 1 minus sine squared. You could either do the u substitution now, or you can go ahead and FOIL out this 1 minus sine squared, all squared. I'll go ahead and do the u substitution now. We're going to let u just be sine, and then du would be cosine x dx. That way the cosine x dx substitutes out just to be the du. So now my integral is going to be that quantity 1 minus u squared, all squared, and then cosine x dx is going to become the du. Now we can FOIL that out a little bit easier. So So that was just multiplying out that parentheses there. Funny looking 4. Sorry about that. And then the antiderivative. So 1 just goes to u. Minus 2u squared is going to go to minus 2/3 u cubed. Plus u to the 4th is going to go to 1/5 u to the 5th plus the constant. And then plug back in u, which was sine. And there we go. So that's going to be the antiderivative. It looks awful, but I promise if you were to take the derivative of this, it would give you cosine to the 5th. Okay, so there's going to be another video here with a couple more examples and then some other techniques for trig.